You could say that I have too many drill bits, and you'd be right. Even if you have only a few spare drill bits, I can show you how to make a storage tray to organize and store your drill bits conveniently in a drawer. You can make some trays using a CNC mill, CNC router, and because I provide the XY coordinates, you can even use a manual mill. Most CNC routers have a dust collector. If you are going to use a milling machine, you can make a simple dust collector using a plastic bottle and a bit of clear shipping tape to keep the machine and work area dust-free. I originally thought of making plastic boxes with a 3D printer, but dismissed the idea. Creating boxes for a complete set of jobber drills would require 29 boxes. 3D printing that many plastic boxes would take all day and require a lot of energy and plastic filament. I decided to make a tray from a slab of wood. Wood has many benefits. It machines quickly, is less expensive, and is a renewable resource. I also thought of using a CAD program to model the drill tray. I wanted my drill bits to fit snugly into custom-sized pockets. Using a CAM program would require having to run 29 G-codes. I decided to create one G-code for each tray using a spreadsheet program. In my last video, I explained how to create a spreadsheet and G-code for cutting pockets. Have a look at that video to learn more about the process. The program I used to make my spreadsheet is called Microsoft Excel. If you do not have this program, you can convert and use my spreadsheet in a free program called Google Sheets. Spreadsheet programs are math wizards. Plus, they allow us to make drawings complete with dimensions that are used as XY coordinates as part of a G-code. This G-code can be copied and pasted into a word processor such as Notepad and loaded into a CNC program. A while ago, I created some spreadsheets. I cut 5 or 6 drill trays and agonized over the fact that my G-codes are very long and cumbersome. I struggled for a long time to make better G-codes using subroutines for you. Fortunately for us, I got some help from a guy who is teaching CNC at a local college. He taught me how to write a structured G-code with subroutines. I wrote new G-codes for my trays. While I was at it, I improved my design, moving the finger pockets to the front of each pocket to make it easier to scoop a drill bit from a pocket. Let me explain the logic of my G-code. 001 is a name I gave to this program. It helps us to stay organized. Anything between the left and right brackets is ignored by the CNC machine's operating system. I included a reminder that the cutter I am using, T1, is a 1/2-inch flat bottom mill. In line N1, G54 is the work offset that I commonly use. Line N2 is a safety line. G90 sets an absolute distance mode. G80 cancels any canned programs that might be stored in the machine's memory. G20 to use inch measurements. G40 turns the cutter radius compensation off, and G17 to use the XY plane. In line N3, the mill cutter moves rapidly to a height of 500 thou above the work surface to avoid crashing the cutter into obstacles. This height can be increased if necessary. In line N4, we center the mill cutter at X.5 and Y.5, where we want to begin our first pocket cut. Line N5 sets the spindle speeds and turns the spindle on. Line N6 is to lower the cutter to Z0 at the top of the work surface and set the feed rate to 30 inches per minute. You can decrease or increase this feed speed if you like. Line N10 contains the code M98P10. Its function is to call a subroutine O10, and L followed by number 4 determines the number of loops the subroutine makes. Let's look at the subroutine O10. First, G91 sets the distance measurement to incremental distances. Second, the mill cutter is lowered minus 150 thou. G90 sets distance measurement back to absolute distances. The feed is set to 30 inches per minute. The next 11 lines, starting with x.86 and ending with y.5, is the XY coordinates for cutting a drill pocket and a finger pocket. M99 completes the loop. The subroutine will repeat 3 more times, cutting the pocket to a depth of 600 thou. With this subroutine complete, the main program runs the next 4 lines. The first line raises the cutter 100 thou above the workpiece. The second line of code rapidly centers the cutter at the starting point of pocket number 2. The third line lowers the cutter to 0. The fourth line calls the next subroutine. This program repeats until all the subroutines are finished. In the last line of subroutines, there is a percent symbol. It is required for some CNC programs to indicate the end of all subroutines. The main program runs the last 2 lines of code, raising the cutter 500 thou above the work surface. M30 stops the spindle, and the program rewinds automatically back to line 1 of the main program. To post a code, left-click and drag the mouse to highlight the G-code cells in the spreadsheet. Once the code has been highlighted, right-click the mouse, select Copy. Open a word processor, such as Notepad. Right-click at the top of the word processor's writing area and select Paste. Using your mouse, select File, Save As, select a destination, then type in a file such as O0001. Select Save, and that's it. You have now created a G-code text file that can be loaded into a CNC program. To make a shallow test cut, set Z0 above the workpiece high enough for the 4th loop to take a thin slice out of each pocket. Or a quicker method is to set Z0 slightly less than 150 thou above the top of the work surface, then change the number of loops from 4 to 1. Here is how I do it. Using Notepad, select Edit, then Replace, type L4 in the box next to the words Find What. In the box next to Replace With, type L1, left-click in Replace All, close the dialog box, save your work to another name such as O000L1, and exit. Load and run the edited L1 code. If you are satisfied with the results, you can now set the cutter Z height to 0 at the top of the work surface. Then run the original O0001 G-code to cut your pockets 600 thou deep. Cutter feed rates and Z height can be changed using the same procedure. After cutting the drill pockets to depth, I changed my 1/2-inch cutting tool to a 5/8-inch chamfer tool. Reset my Z0 so that the chamfer tool's edge just touched the side of a pocket. I edited my G-code to run just 1 loop. This created a smooth bevel along the top edges of my drill pockets. It is not necessary. I did not bevel all of my drill trays. Each one of my drill trays is roughly 5 1/4 by 23 inches. My mill table is limited to cut 5 3/8 on the y-axis and 27 inches on the x-axis. My rough boards are 5.5 by 27.5 inches. I measure the distance from the edge of my table to the center of each T-nut slot that I will be using. Using that measurement, I lay out 2 hole locations as close as possible to the ends of my board and centered on my mill table. After laying out the hole locations, I drilled each hole with a 9/16 spade bit. To mount the board safely above the mill table, I used 3/4 inch pieces of plywood at each end and one in the middle. I fastened the board with 2 1/2-inch cap head bolts. Before tightening, I do a rough tram to align the edge of the board parallel to the edge of the table. Then I tighten the bolts reasonably tight. After milling the pockets, I trim the boards to size with a saw to fit them in my drawer. These trays are designed to fit into a 22 7/8 inch drawer. If your drawers are not quite long enough or wide enough, you can reduce the size of each drill tray. You can reduce the thickness of the webs between each pocket. Changing the number in this cell changes the width of each web. We can also reduce the width of each pocket and reduce the length of each pocket. The first 2 drill trays can be reduced easily by reducing the length of the spare pockets. Let me show you how to reduce the length of the other pockets by editing the drill chart. This is the current length of the tray. In the drill chart, I click in the first cell. Written in it is 2.18. This number is the length of this drill pocket. If we look above in the formula bar, we see that the formula for setting this pocket length is T36 plus 0.375. Written in cell T36 is 1.80. The drill length for a 1/16 inch drill. To make the drill pocket smaller, we change 0.375 to a smaller number. I am changing 0.375 to 0.30, then pressing enter. Now that I have changed the formula in this cell, I will copy this formula down to the rest of the cells. I place my cursor on the cell that I want to copy, grab onto the small square, and drag the square down to the bottom of the column. I let go of the left mouse button and voila, all the pockets are shorter. Now, when the tray is cut, the end-to-end measurement will be 22.52 inches. Wood is fairly easy to mill, but if you use a larger cutter, deeper depth of cut, and faster feed speeds, you risk the chance of blowing out the thin wall of the finger pockets. I cut out different types of wood for my trays. I made a tray from a 2x6 plank. I milled the crown off the top surface beforehand. I made trays using a particle board and melamine coated MDF. Afterwards, I labeled my drill pockets with a Sharpie. Actually, my wife was kind enough to label them for me. Her writing skills are far superior to mine. I started filling in my trays. It took me a while to sort through all of my drill bits. Many were illegible due to wear and tear. I found the easiest way to sort my older bits was to use a drill index and a vernier caliper. There you have it. That is how you make 2 different sets of drill bit trays from wood using a spreadsheet and subroutines. I hope you liked the video. Please give me a thumbs up, subscribe, and share if you'd like to see more of my videos. I learned many lessons making this project. I hope you learned something too and found this video useful. If you would like to download a copy of my spreadsheet, I placed a link in my comment down below. And once again, thanks for watching.